Students of the internet era approach learning differently than their predecessors. Typically they believe that all the world's information is at their fingertips, so they don't need to memorize anything. Note-taking is a lost art, and textbooks are viewed as unnecessary. Instead, video is their preferred information source. There is a vast number of these educational videos online. And students like watching these videos, especially those with some entertainment value. But watching them is a very passive process that often leads to the illusion of knowledge. The illusion of knowledge is the belief that you have mastered a topic, when in fact, you haven't. Students suffering from this illusion often confuse superficial familiarity with true knowledge or actual understanding. Unfortunately, this means they don't know what they don't know until it's too late. For their part, some instructors are happy to use these educational videos or to record their existing lectures onto video and then skip directly to the evaluation part of their job. But simply broadcasting educational videos, or lecture recordings, doesn't equal teaching. If it did, we could just send all our students over to YouTube and call it good. So, no matter what their discipline or preferred method of instruction, it's clear that teachers should provide activities that fill the gap between their instruction and student evaluation. After all, you could argue that this is where real learning occurs anyway. Specifically, teachers should be creating opportunities for students to practice, problem solve and self-evaluate while having meaningful and timely feedback available to them. To be taken seriously by today's students, these exercises must be interactive, time-efficient, and engaging. This video describes one kind of practice and feedback activity that fits this description. This multimedia example was built using tried and tested learning science and is designed to be attractive and helpful to students and instructors alike. Because we are concerned with learning and cognition, we want to incorporate the most effective learning strategies in these exercises. The cognitive science literature includes many possibilities. Things such as retrieval practice, dual coding, and elaboration are devices we could employ. Retrieval practice or self-testing is the ability of a student to quiz themselves in a way that enhances learning. The educational research literature suggests that self-testing is the one thing that best predicts student success at all levels. Run-of-the-mill flashcards are a simple example of a self-testing tool. Review questions that you might find at the end of a textbook chapter are another. In fact, the kind of module we've developed here is often called a self-testing tool. So, you're probably wondering how this kind of app is better than flashcards and regular review questions? Well, let me explain. To start, these modules do more than just add images and videos. They include physical activities and auditory experiences as well. Complex animations and simulations together with case studies can also be included where appropriate. When you develop a tool like this, you want the user to concentrate on the content, not the tool. In scientific terms, you want to minimize the cognitive load introduced by the user interface by employing the most uncomplicated design possible. Users should have a clear path through your app. They should never be left guessing what they should do next. We do this with a consistent but straightforward navigation scheme, uniform placement of controls, and hiding supporting or supplementary information until it's appropriate to display it. After your user interface has been optimized, you want to maximize the degree of user interactivity in each scene. We do this by employing a range of interactive question types. There are no thinly disguised multi-choice questions here. Instead, our question types include such things as regional and structure-based selections. Image-based multi-choice questions like this lesioning exercise from the brachial plexus. Multi-label drag-and-drop exercises such as this example examining the vasculature of the neck. Or simple painting or drawing exercises like this activity that requires students to identify hemidesmosomes. And my favorite, correlated drawing across multiple images. These images could involve reconciling structures from textbook images with real histological sections. Or it could involve comparing an X-ray with a cadaver image. Or even identifying structures in two different views of the same specimen. Another way that these exercises are better is the approach we employ for providing user feedback. Each question is accompanied by extensive feedback in the form of heavily annotated images and answers. Both right and wrong answers are annotated by design. Our beta testing exposed how students viewed all answers anyway, even the wrong ones, provided we included a detailed explanation. So we incorporated this in a strategy we call, if right, show all answers. This is important because after answering a question, users are often primed for more information. In addition to these annotated answers, we also supply supplementary information in the form of high-yield infographics. These infographics reduce the key information students need to know into a single page or screen full of content. Students really like when information is presented in this way, but we only make these infographics available after a user has first attempted the corresponding question. Another cognitive strategy implemented here addresses how knowledge is developed. We know, for instance, that there are different kinds of knowledge and that each successive capability builds on prior learning and experience, an idea commonly expressed in Bloom's pyramid. We use this idea to construct a series of questions with increasing difficulty and organize them into discrete sections addressing different capabilities. In the anatomy versions of this app, we use 4 question types that test these different capabilities. We term these different stages: simple, identify, structure, function, similar or nearby, and apply or integrate. We encourage users to start at the most foundational levels, but they can choose any order they desire based on their personal preference. In fact, we allow multiple different starting points. This means individual users can navigate a different path through these exercises that depends on their own level of prior knowledge and familiarity with the material. So how do you know whether or not your students are using these activities? Well, we have built extensive analytics into these exercises that help us measure student engagement and performance. These background analytics record many different interaction types each time a student uses this app. In fact, every time a student interacts with one of these exercises, an event is triggered and captured in a remote database. These data can be mined on the whole class level to get comprehensive engagement data or per session to track how a particular student is navigating the activity. While anonymized, this data can be analyzed for trends and potential deficits that might require remediation. When we examine these statistics from multiple instances of this app, they indicate large-scale engagement over significant periods of time and a high level of progress towards completion. So this has been a very brief introduction to the educational apps we have built at AlteredMindWare. There is a lot more going on behind the scenes that we didn't have time to show in this short video. If you are interested to learn more, please contact us at the address below for further details.